assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
In this example, we have this system here where a metal bar is sliding along these wires that are making an angle with each other of 19 degrees. And it's completing a circuit with these two wires that is shaped like a triangle. So you can see if we started go up to the bar here, down and then back, we have a triangle. And you can see that the area of that triangle is going to change as our bar slides to the right. The area will be getting greater. Now, correspondingly, since this configuration here is sitting in a uniform constant magnetic field, we will also be increasing the total flux through our loop here, our little triangle loop, because of the fact that we're changing the area of our loop. And what we want to figure out is what is our induced EMF because of that change in flux we're introducing 6 seconds after our rod here passes point A when it's moving at 0.6 meters per second. Okay, so the first thing to recall is Faraday's law of induction, which just states that the induced EMF is going to be equal to the change in magnetic flux over the change in time. And our change in magnetic flux here is going to be from the point at which our bar passes A, which is when we have no flux, to when it's at some further point out, 6 seconds later on. So really, this is going to be the average EMF, since we're just looking at two different points in time and using the change in flux from A out to this new point in time. All right, so the change in flux is just going to be our final flux minus our initial flux, where our initial flux is going to be 0 because we have no area in our triangle at the start, right? In general, our equation for the flux is going to be B times A times the cosine of the angle between the magnetic field and our surface normal, which in this case is just going to be 0 at all times. So the flux is just going to be B times A, where in this case, this is the area of a triangle. So it's going to be B times 1/2 base times height, which is the area of a triangle, where the base and the height are going to change with time. But anyway, so the initial flux we said is going to be 0, and the final flux is just going to be equal to this expression here we wrote for the general flux, where we'll have to figure out what this base and this height are going to be. So our change in flux is just going to be B times little b times h over 2, where these are the base and height of our triangle at 6 seconds. Okay, so let's figure out what those are so that we can plug this back into our equation here for the induced EMF. So if we draw our triangle, we know that this angle here is 19 degrees, but we don't know what the base is and we don't know what the height is. However, we do know that this bar is traveling at a constant rate of 6 meters per second, or 0.6 meters per second. So horizontally, it's just going to travel a distance of its velocity times the change in time, right? Remember back to mechanics, velocity is just equal to the change in distance over the change in time. Or if we solve that for x, we'll have the change in distance is just equal to v times t. So really, b here, little b, is just going to be equal to V times our delta t, which in this case, delta t is 6 seconds, and V is 0.6 meters per second. So B should be equal to 3.6 meters. And now that we have B, and we have this angle 19 degrees here, we can determine what H is by using the tangent function. So we know that the tangent of 19 degrees is going to be equal to the opposite side over the adjacent side, which is H over B. Let's move down here so we have a little more room. So tan of 19 is H over B. If we multiply both sides of that equation by B, we'll have H is equal to B times tan of 19 degrees, which if we plug in all our values is just going to be 1.24 meters. All right. So now, since we have little b and little h here in our equation for the flux, we should have everything we need to calculate our induced EMF. So let's write out what our final equation is going to be. The induced EMF is equal to minus the change in flux over the change in time, where our change in flux is just B times 1/2 BH. So we'll have minus B times little b times H over 2 over delta T. So I'll have a 2 times delta T in the denominator there. So we know delta T is just 6 seconds, H is 1.24 meters, B is 3.6 meters, and the strength of the field is 0.38 Tesla. We can just plug all of our values in. And if we ignore the sign, we'll have that the magnitude of our induced EMF is just equal to 0.14 volts. So we just determined what the magnitude of the induced EMF was in our little triangular loop here. And the induced EMF came from the fact that the area of our loop was growing in this constant magnetic field, which means that there was an increase in magnetic flux through our loop, thus implying a induced EMF.